In this week's experiment, we're going to be studying acceleration. So we've got a little cart on the track, and to accelerate it, we've attached a little fan. So for example, if I turn this on and release it, it's going to accelerate the cart down the track on its own. Do watch your fingers with those fans. They kind of sting when you get your hand caught in it. I'm going to show you separately how to use the program that we use this week. So for now, I'm just going to show you what you do with the physical cart and track. So to begin with, anytime we use the track, you need to level the track first. So I'm going to pause now and let you watch a little bit of video that shows you how to level your track correctly. Anytime you're using the cart on the tracks, you want to make sure that your track is well leveled before you start taking data. So the first thing you do is try and rock the track back and forth horizontally. It shouldn't wobble. If it does, adjust your legs so that it's nice and stable to begin with. Then you want to adjust them higher or lower on one end in order to level the whole track. We have this bubble level, and you just lie it flat on the track, and I'll show you a close-up in a moment, and adjust the legs such that the bubble in the middle of the bubble level is centered between its two lines. And if I zoom in a little bit, you can see that the bubble is centered between its two lines. And if I come down the track a little bit, this bubble also is relatively centered between its two lines. So now that you've got your track leveled, you're going to start with the experiment. So question 1, we're actually going to do 4 cases with this fan cart. Question 1, they say if you take your fan cart, and start it from rest at the origin and release it in the positive direction down the track, what happens to its position and its velocity? Now, first of all, recall that for our purposes, the origin is at the end of the dead zone. So you need to start your cart at least 15 centimeters away from the sensor. For part A, for question A, they're asking you what the cart does. So just what the cart does. In question B, they're going to ask you what happens on the graphs. They ask you to actually make a prediction. So they have spaces for you to sketch in a position time graph and a velocity time graph. And you're supposed to sketch in the ideal case, what would happen in a perfect world if there was no friction, no bumps on the track, nothing like that. So based on the theory you've learned in class, you sketch in your prediction for what's the position time graph and the velocity time graph for this cart are going to look like. In part C, you actually take data using the program, and then you're going to compare it back to what you saw in your predictions. So you would capture the data on the screen. Like I said, I'm going to show you that in a moment. And then you'll compare back to the predictions you made. One of the things you're going to want to do, by the way, is fit a straight line through your second graph, the velocity time graph, in order to get the acceleration that's being given by the fan. Question D, for question 1, says briefly comment on the similarities and differences between your prediction, so the graphs you sketched, and the observed graphs, so the ones you got off the screen. To get full marks for this, you need to talk about similarities and differences. And also, when you talk about the similarities, it's not enough to say your graphs looked the same. You need to be very specific. Use graphing language. So say things like, they were both linear, or they were both curved upward. The slope was positive, the slope was negative. Maybe talk about the y-intercept. So use graphing language to talk about how they're the same, and then also talk about how they're different. So, for example, the real-world case usually has some bumps and wiggles due to imperfections of the track, and maybe some friction effects, which would be curvature when you don't expect to see curvature. So make sure that you comment on similarities and differences for part D. All of the files that you're going to need this semester will be in the 1100 folder on your desktop. So you can go ahead and open up that 1100 folder. And last week we used the velocity program. This week we're going to use the acceleration program. So go ahead and open that up. Now the first thing you notice is that we have 2 graphs this time. So last week we just had a position time graph. This week we've got position time graph and also a velocity time graph. Now we're studying acceleration today, constant acceleration. On a position time graph, we expect constant acceleration to look like a curved line because the velocity is increasing every second. However, on a velocity time graph, we expect constant acceleration to result in a straight line. So the velocity increases at a constant rate every second. That's what constant acceleration is. So we expect to see a nice straight line here. Now I'm going to actually demonstrate this for you, so this will get a little bit noisy, just bear with me. What I'll need to do is turn on the fan cart, then I'll press this collect button to start taking data, and then I'll release the fan cart and just let it accelerate down the track. So one moment please. So one thing you'll notice right away is that yes, as expected, acceleration did look like a curved line on this position time graph. However, velocity time doesn't look like much of anything. The reason why is that the scale is too big for the amount of acceleration that we had, the velocity changes we had. So you can just hover your mouse over top of the tick marks on the axis and then click and drag it, but quite honestly that takes quite a bit of time. So instead what I'd recommend you do is click on the top number, whatever it is, and it will allow you to change what the highest number on this scale is. So I'm going to change this to 1. Hit enter. Okay, that helped a lot. I also want to get rid of a whole bunch of this. So again, I'll click on the lowest number. So I'll make that negative 0.1, let's say. And now it's starting to look the way we want it to. But I'm going to stretch it out just a little bit more. So again, you click on the highest number and then change it to whatever value you want. So I'll say 0.5, enter. And now I can see that yes, this basically looks like a nice linear graph, which is what I expected for constant acceleration. We've got a little bit of bumpiness. That's totally normal. It's just due to little imperfections in the track itself. The next thing we're going to want to do is actually fit a straight line through this, because we want the slope value. That's our acceleration. We need that. The way in which you do it is you first of all highlight a section of data that looks pretty linear. Go ahead and just avoid the little bumps and wiggles. Choose a section that's quite linear, and then there's two ways to get the fit. You can go up here to Analyze and go Analyze Linear Fit. It will plot a straight line through the section of data that you highlighted. And if you decide you don't like it, you can also get rid of it with the little X. You can also highlight another section of data if you weren't happy with the first one. Like I said, there's two ways to get the fit. The first is, as I said, Analyze Linear Fit. There's also a little button up here at the top that will give you a linear fit. So I go Linear Fit, and I put it on there. And I can move that box to wherever it's handy and then print things out. Now when you're completely done with the program, and you're actually going to be using this program 4 times during the lab, so it won't be for a while, but when you're done with things, you should click the little X to close it down. It will always ask you, do you want to save the changes? Say no. We don't actually want to save anything that we did here. We're going to be studying 4 different cases today. So the first one was that you started the cart from rest at the origin, so the edge of the dead zone, and just let it accelerate freely down the track. Second case is question 2 in your manual. You want to do the same thing, let it freely accelerate down the track, except they want you to arrange to have an initial velocity. So how do we actually do that? What we do is we just start the cart inside the dead zone. The idea is you turn on this fan, and by the time it gets to 15 centimeters, so that by the time it gets to the point where the computer can actually track it, it's going to have an initial velocity. So to do this one, you would just start it inside the dead zone, turn on the fan, and let it accelerate freely. So turn it on, start your program, let it go. So it had an initial velocity when it got to here. And as before, question A, for question 2, question A is describe what the cart physically did in terms of its position and its velocity. Question B is sketch your predicted shape for the position time and velocity time graphs. Question C is you actually capture the data on the screen, print out your graphs with a fit to the second graph, your velocity time graph, paste it into your book. And question D is talk about what's the same, what's different between your printed graphs and the predictions that you sketched in your lab book. Okay, so now we're ready to try the third case. This one's a little bit tricky to do. What we're going to do is we're going to actually start the cart down here at the end of the track. We're going to give it a little bit of a push towards the sensor, so a negative velocity towards the sensor. The acceleration of the fan, of course, is still in the positive direction. So what's going to happen is we're going to start down here, give it a push this way, and the fan will actually turn the cart around and it'll start accelerating down the track again. So it looks a little like this. Turn it on, give it a little push, and it'll turn itself around. Now there's something about this particular case and our apparatus which may give you something you don't theoretically expect to see. So I'm going to show you what it looks like on screen now. Alright, this is what we expect to see, spoiler alert, for the third case, where the cart actually changed direction. So we pushed the cart towards the sensor, it was moving in the negative direction, and then the strength of the fan, the acceleration, turned it around and it started moving away from the sensor again. So as usual, acceleration on a position time graph looks like a curved line. So it started out going in the negative direction, so the position got smaller, and then it turned around and it started going in the positive direction. So the position started to become a bigger number. On the velocity time graph, we still expect to see a perfectly linear line because the fan did not magically get stronger or weaker during the experiment. So it should still keep giving us constant acceleration. That means we should get a perfectly straight line. It's quite possible that on your equipment that's what you saw, that this line is perfectly straight. But it's very common with our equipment to sometimes see a kink in the data, basically meaning that the line down here isn't quite parallel to the line up here. Now, first though, I'm just going to explain that when we were moving towards a sensor, that's a negative direction, so we have a negative velocity. That's why the velocity down here is below zero. And once it turned around, we're now moving away from the sensor, that's the positive direction, so we have a positive velocity. This line is above zero. So, as I said, theoretically we expect to see a perfectly straight line, but if I actually highlight the data down here and fit it, and then highlight another section of data up here, where the cart had turned around and was going in the positive direction again, and fit that also, that you can clearly see that it changed slope. So that means that the magnitude of the acceleration changed when the cart changed direction. That's not supposed to happen, but with our equipment it's fairly common for it to happen, so you need to watch out and find out whether it happened on yours. So if you see a perfectly straight line, great. Just fit it as normal, print it out. But if you see any hint of this kink in the data, then fit it the way I have here, where you fit a section below zero when you had a negative velocity, and above zero when you had a positive velocity, and then print out the graph like this with two fits on it. The reason why is that if you look at the very last page, last question of the lab manual, question 11, it says, did you notice any difference in the acceleration magnitude related to the direction of motion? So what they're fishing for is basically, did you see this kink in the data? That the acceleration magnitude seemed to change when the cart changed direction. If you did, then you would say, yes I did, and then you want to try and explain why that might have happened. So the fan did not change strength, what caused the acceleration to change? And finally, case 4. So question 4, what we do in this case is we take the cart and we turn it around backwards, and we'll start it right at the end of the track here and let it accelerate toward the sensor. So be a little careful to grab it before it actually crashes into the sensor, but basically this is the motion we want to capture with the computer program. You turn it on, you release it, it accelerates toward the sensor, and then try and catch it before you actually have a collision. Okay, so when you get to question 5, there's some questions here that some students find a little bit tricky, so I'm going to give you some hints here. So question 5 is, describe a real-world situation where the acceleration is either in the same direction as the direction of motion, or the acceleration is in the opposite direction to the direction of motion. So with the cart on the track, we studied both of these. We had cases where the acceleration and the velocity were both headed in the same direction, and that third case, to begin with at least, we had the acceleration being in the positive direction, but the initial velocity being in the negative direction. So you looked at these. So now you just need to think of real-world situations where that similar state of affairs exists. So think about throwing a ball in the air or stuff like that. Second question, or pardon me, the sixth question says, using the apparatus provided, so the same cart, fan, and track that we had, how could you get an acceleration that was larger than what we measured, or an acceleration that was smaller than what we measured? So think about how you could tweak the track, for example, to make the acceleration larger or smaller, or the cart itself, or the fan itself. So there's more than one answer for how you can do this. Question 7 says, describe a real-world situation where an object has a large acceleration but a small velocity, or a small acceleration but a large velocity. So think about things like a rocket ship taking off, or a car coasting on the highway. Try and think of a situation where the acceleration might be huge but the velocity isn't very big yet. Or you have a small acceleration but it's actually going really fast too. So just try and think of something like that. Question 8 says, using your data and your fit lines, find a value for the acceleration for the 4 cases that we studied. By the time you get here, you've already got these numbers. You should not need to do any calculations. You should be able to just write down the numbers. Questions 9 and 10 are sort of related. Why are the first 3 measured accelerations listed all positive, and which acceleration magnitudes roughly agree with each other? Can't give you an answer for this, but what I will say is the thing to remember when you're trying to answer this is that we only had one fan. So all of our accelerations came from that one device. So if you keep that in mind, it becomes a little easier to answer these questions. And the last question, did you notice any difference in the acceleration magnitude related to the direction of motion? As I hinted earlier, that has to do with that third case where the cart changed direction. Did you see a kink in the data? And if so, what could have caused that?